let's now consider the class of flows called potential flows. To start with our understanding of potential flows, let's recall that for an ideal fluid, we have a vorticity equation. And the vorticity equation for an ideal fluid is that d by dt of the vorticity is equal to del cross u cross omega. And this is the various nonlinear interactions between the vorticity and the velocity, the shear stretching terms, the advection terms, and also the compressible amplification terms. Now, we know from this, if omega is ever zero, then since the time derivative of omega is given itself by the nonlinear product of velocity with omega, we know that if omega is ever zero, then the vorticity is zero for all time. There's no way to generate vorticity in this ideal fluid equation set where we're also, our other assumption here was that we have conservative forces. If we have conservative forces and no viscosity, there's no way to generate the vorticity whatsoever. And this gives us the class of irrotational flows. And for irrotational, so irrotational flows are of some real interest. What can we do about irrotational flows and modeling them? Well, our irrotational flows, right? So these are flows where the vorticity is zero. And the vorticity, recall, is always given by the curl of the velocity u. So if we want the vorticity to be zero no matter what, let's represent u as the negative gradient of some scalar function, because then by vector calculus, the curl of the grad of anything is zero for any version of that thing, no matter what it is. So our scalar potential can be whatever it wants, and it will ensure that the flow is always irrotational. This is our potential. This is sort of the opposite. This is a different version of what we saw with incompressible flows, where we took a stream function. Here, since we have an irrotational flow, we take a potential, and we call this a potential flow. So in sort of similar ways, potential flows are extremely good for describing irrotational fluids. If our flow is incompressible and irrotational, if it's irrotational and incompressible, then we can see that the divergence of u being zero, well, this implies that the by our definition of the flow being given by a potential, this means that the divergence of the negative gradient of phi is zero. This means that the Laplacian of phi is equal to zero, which means that the potential satisfies what's called Laplace's equation. And solutions to Laplace's equation, these are sort of the bread and butter of a lot of Fourier analysis and of math solutions. Once you know the boundary conditions, you know the solutions for a huge class of Laplace equations. And so you can really get at a lot of flows because the Laplace's equation gives you the potential phi, then you take minus its gradient to get the velocity vectors u, and you're off to the races. So this is a powerful way of solving flows that are both irrotational and incompressible at the same time.